we're finishing up the last lesson, and then we'll jump into what we talked about with the pre-quiz. So this is a review question right here. This is not something new. Show your neighbor, tell them what the answer is. Correct answer is E. Hold your right hand rule number 1 or 2? 1. Okay. You're looking at the magnetic field that this guy is creating. Goes around like this. You let go at point P into the board. Circle with an X. Good with that? Okay. Now, that's going to set the stage for the next question. Okay. At point P, the field is going, the magnetic field that this produces is going into the board. We're going to set a secondary wire, another wire in this vicinity at point P. What I want to know is, what is the direction of the magnetic force on this second wire because it's in the magnetic field produced by this first wire? Tell and show your neighbor.
Do you know why brain freezes happen?
I don't. Possible.
I need it.
Okay, what do you say? Correct answer is Buster Brown. B. Here's why. So here we had a magnetic field going into the board from this guy. So my fingers, so this is the external field that that wire 2 finds itself in. So my fingers are going to go into the board. Okay. Current goes in the direction, my thumb goes in the direction of current. Okay. And so the wire gets forced up. Okay. If you are good with that, and that makes sense to you, you have no problems with that, go with that. If you're good with this, just close your ears. If you're like, oh, what are electrons? Okay. We'll have a realist conversation. So there's a magnetic field. The electrons are going the opposite direction of current. So you got to watch that, and they're negatively charged to going up. Okay. My suggestion would be, if you're good with Ben Franklin follower, a conventionalist, physics is set up for you. Okay, if you're not sure which one to be, follow Ben. Okay, follow Ben Franklin. Be a conventionalist. Okay, but if you're gonna be a realist, you gotta go all the way. Yep. All right, now we just went through this progression. I want you to go through that same progression, but this time I want to know what is the direction on wire 1 because of the magnetic field from wire 2. Hold on to your own thoughts. I'll give you a chance to converse momentarily. Have a conversation. Show them, talk them through it. Okay. Correct answer is A. It is the correct answer. Okay. Here we go. So we're looking at this one. This is creating its own magnetic field. So at where this is located, it's coming out of the board. So my fingers are going out of the board here. Okay. In wire 1, the current's going this way to the right. So I'm going to stick my thumb to the right and force down. Okay. Good with that? I'll walk it through again. Magnetic field by wire 2. It produces that magnetic field at this location where wire 1 is. That's coming out of the board. So now this out of the board, it becomes the external magnetic field that this guy's in. Using right hand rule number 2 to experience a force. Got external magnetic field coming out of the page. Thumb's going to the right with the direction of current, being forced down. Okay. If that makes sense to you, go with it. If you're a realist and you're like, well, electrons, but they're going the opposite direction of motion over the current. Down. Okay. All right. So that's that. Moving on to lesson 4. Okay. So, okay, may I introduce you to a galvanometer? Okay. And got a solenoid. Okay. I'm going to hook these up together. Okay. This this galvanometer. Some guy with the last name Galvin made it. Okay. But it measures small amounts of current. What does this measure? Small amounts of current. Okay. I'm going to take this solenoid, which all this is a wire wrapped around, we'll just say, a toilet paper tube. Okay, that's all it is. I'm going to connect that to the galvanometer. Okay. Now, is this a complete circuit? Is this a complete circuit? It is a complete circuit. Okay, it's a full loop. Okay. Now, is there any power supply to this circuit? No, it's just a wire connected to a galvanometer. Okay, this is not. There's no power going in. This is not battery operated. Okay, it's just a meter that measures small amounts of current. Let's say we took our magnet and we happened to run it through. We were just playing around with the magnet one day and like, woo, whoa, that's crazy. Huh. Just, what? That's nuts. Like what? What? Like what happens if you do? Whoa, crazy. What? Like how? What is this? What is this measuring again? Small amounts of current. Let's say you just discovered this back in like the 1850s. What could you do with this as a proof of concept? And you're entrepreneurial. What could you do so that your great 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 grandkids nowadays would be quadrillionaires with this idea? Why? What would you patent it for? Like, what would you sell it as? You are producing electricity. Prior to this, electricity only came from batteries, which required chemicals and were expensive. Still are expensive. But this, we just created, oop, broke the circuit. We just created electricity simply by moving a magnet through a coil of wire. Crazy. Good with that? JP. It, they are doing stuff with, they're trying to do one with like superconducting. That's what I think. I'm not sure. Maybe. The one that I'm aware of that they're trying to make is one with superconductors and using like levitation with magnets. I don't know if it's the same one you've heard of. Okay, so now here's the idea. Faraday came up with this idea that if a conductor experiences a changing magnetic field, and this is from the pre-video or the pre-quiz, changing magnetic field, then voltage is induced across the conductor, and if that conductor is wired in a complete circuit, then current is induced. Induced and created, they're synonyms. Okay. Now, let's say, so here, this conductor experienced a change in magnetic field. Here, no magnetic field, all of a sudden magnetic field, and then no magnetic field. This experienced a change in magnetic field as this magnet was brought near it. But you can also have a conductor experiences a change in magnetic field by, we take our big horseshoe magnet and watch the needle behind my hands. It moves ever so slightly. Moves ever so slightly. I don't know if you can see that from there. Not very dramatic. But there you go. Okay. Could light a little bitty light bulb. Not really. Couldn't even do that. But the idea is there. Try with that. Okay. So if it experiences a change in magnetic field, then current is created. Now, it kind of seems magical. So let's understand how that actually works. All right, so first off, you need a magnetic field. We got one. Where did that come from? Let's pretend we have this ginormous horseshoe magnet. Okay. North pole, south pole, magnetic field lines go out of north into south. Let's say we take this and we put the south pole behind the board, and north pole is over here, so magnetic field is going out of north into south. Magnetic field. Okay. And then we have this conductor. We're going to say copper. Is copper magnetic? Copper is not magnetic. It's not iron, nickel, or cobalt. Okay. So it's not going to stick to the magnet. But what it does have are a bunch of protons and electrons. Okay. Now, let's say, are these charged particles going to do anything if they're just sitting inside the magnetic field? Nope. But if I come along and I grab a hold of this thing and I pull it with a certain velocity, all of a sudden, all those charged particles are along for the ride. Good with that? Now, which ones are free to move? Electrons. Which way are electrons going to be forced because they're now moving in a magnetic field? Show your neighbor. Which way are electrons going to be forced? Nope. So when you're dealing with particles, your thumb is the direction of velocity. When you're dealing with a wire with current, your thumb is the direction of current. Current then. We don't have current yet. We're talking about a particle, so this is your thumb is the direction of velocity of a particle. Yeah. Okay. Okay. A question that came up. It's a good question. I thought, which way is current going? I thought my thumb was current. It is when you're talking about a wire with current flowing through it. But if you're talking about charged particles, your thumb is the velocity. Okay. So here we're talking about charged particles, so our thumb is velocity. My finger's going into the board, magnetic field. this thing's moving this way, so all the charged particles have a velocity to the right, direction of the thumb. So electrons are negatively charged, they're forced downward. Okay? So the consequence of that is you've got this conductor, protons are just there, but the electrons are being forced down. If you were an electron, where would you rather be? Top or bottom? On the top. Do you see there's a motivation to be somewhere else? Kind of like we have a battery. Kind of like there's an electric potential difference from one spot to the next. Kind of like there's a voltage across this. That's the induced voltage. Okay. Do we have current yet? Nope. We just have electrons motivated. Okay. Now, if we were to give an option, i.e. a circuit, what would happen? And this was continue to move. Electrons are like, yeah, come on. Bing. Light goes on. Now, what happens when the electrons get back in here? They're like, ah! They're forced again. Does that make sense? Is there current now? Yes, because we hooked that up to complete circuit. Which way is that current by definition? Thanks to Ben Franklin. Current is in the opposite direction of electron flow. All right, with that, JP. What?
There's no battery, right?
Yep.
So it can't run out.
Right.
So it's endless electricity.
Endless electricity. Pretty cool invention. That's why your great great grandkids would be trillionaires.
Do we do that now?
Great question. Yes, we do. So what would happen if we stopped this conductor? Right, because electrons would be like, why am I here? Get it moving. You're like, ah! You have to be moving. Okay. And yeah, we'll get to that. We'll hit that tomorrow. But yeah, that's a whole half day. We will talk. If you think you come up with something like that's too good to be true, you have. We'll, there's something. We'll talk about it. Okay. But until that point, oh, here, hold on. That's there. You don't need that. What? Take a picture of that. Well, okay. Okay. Some people have hard time with this. We're looking down on top of the plane, so this is the right. This is the left wing. Talk to your neighbor. Show them.
Oh, right. Wait, no, I see. Okay, B, right. B makes, it makes sense in my head. True, like, well, I thought it would be, that's how it goes. Yes. I like that. And look at me going to
Okay. Correct answer is? Good. B. Buster Brown. So going to the left, fingers going in. Electrons get forced back of the hand. So this is positive. Okay. That's the way the plane is flying. You good with that? So everything's along for the ride. All the charged particles.
I got a joke for right. It's like Lexi.
Talk to your neighbor.
I'm never good at this class.
Okay. Trick question. Correct answer is C. Why not?
Oh, I know, because there's no circuit.
Because it's not connected to a circuit. There is an induced voltage. Okay, electrons are motivated, but in order to get a current, you need a circuit.
Okay,
So now it is wired in a circuit.
so it's the other way. Yes. Okay. Wait, I have a question. When, like, you're doing the thing where it's like this, and so this way is electrons. Are they moving that way, or do they start that way?
Oh, good question.
Like,
They're being pushed
They're
this
being
way.
pushed that way?
Yeah.
Okay. You're right.
Okay. Tell your neighbor.
I still don't know. That's so embarrassing. Was it just that original thing, or does it like? That's so embarrassing. I think it'll just get confused.
Okay. Tell your neighbor.
The electrons get confused. I don't know what it says. What happens if you like move it up and down?
Great question. That's the next slide. Okay. Correct answer is electrons get forced this way. So electrons are going this way. Protons go this way. Sorry, current goes by definition the other way. Okay, so the correct answer is the left. Okay, hold your fingers this way. Electrons are being forced. They're moving this way. They're being forced this way. So it's going around like this. Okay. Now, The magnetic field's going in. They're being pulled this way. It's moving up. So they're moving through this magnetic field. They experience a force this way. Okay, so if you want to go, if you want to be like full on Ben Franklin follower, you just kind of pretend that protons move, because that's what he thought. And this is in the direction of current. Okay, all right. Now, so let's pretend this is hooked up. This is my conductor. Let's pretend it's hooked up to the circuit. Okay. As we pull it through, current's created. This is hooked up to the circuit. But once I run out of magnetic field, will that be the case? No. Stink. I need a really big magnet. Yes. This goes on. Really long. Sounds expensive and unrealistic. So, what would happen if I went back the other way? What would the consequence to that be? Would current be induced? Would current be created? If it's hooked up to a circuit, yes. What's the consequence, though? What would be the consequence of me going this way? Opposite. No, yes. I don't know if you get. What's my consequence of going this way? What is good? The current goes the other way. Okay, listen up. Oh, about smacked some ruler. That was hilarious. Okay. Okay. I have current going the opposite way. Does that still light light bulbs? Yes. That seems like a really good alternative to an infinitely long magnet. So if I do this, I can light a light bulb. Okay? If I do this faster, my flickering, it will still flicker like, okay? But if I go up faster, kind of like a flip book, I can prevent that from getting dim and just on, okay? In the United States, we do this 60 times a second. I think I know what your question is. I'm going to hold off on that momentarily, okay? So this mechanically is really rough. So what we do, instead of doing this, we go, watch the shadow, we go in a circle. You see how the shadow is just going back and forth, just like doing this? This, mechanically, is way smoother. I can do this easy, 60 times a second. Okay? We have things that spin way faster than 60 times a second. Okay? JP, question. That's what I thought. Why would we not spin it? Okay? No, we did not do that from the last. Like resistance wise? Not totally. Okay, now, one last thing. This back and forth current is known as alternating current. Okay? Up until this point, I've led you to believe that all current is direct current, DC. It flows out of positive into negative. That's what I've taught you. These come from batteries and solar panels. This goes back and forth from generators. So the follow-up question for the video is the stuff in the outlet AC or is it DC?
DC. DC.
We'll talk about it tomorrow.